Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi. We have a lot of time, so please stop me whenever something is not clear. So today I'm going to talk about this new model for coding, the found model. We'll see like efficient implementations of this model, which has the standard implementations are for the erasure channel. Then we will look into the generalizations, which is sort of the new word, to channels which have errors, general channels, not only erasures. And then finally, we will see how codes that have been designed for erasure channel would work for other channels. So, the main problem which sort of motivates founding codes is a problem that we have probably the file, and we want to send it to a lot of receivers. So, but these receivers have different kind of channels, and so what we want to do is efficiently, we want to do it so that on the server side there's not much burden for sending all this information, and at the same time all the receivers receive it quite fast. So the main problem is that usually we don't know the quality of these channels on which we are sending. Sometimes, I mean, there is not a pre-known quality. For example, over the internet, sometimes something is good, sometimes it's bad, so it's even dependent on time. But we are ambitious, so we want to send it at a rate which is close to the capacity of the channel. And we want it to be the case that when we have a lot of channels, then still we can transmit it. I mean, with just one server, we can service a lot of people. But the main problem is, I mean, one solution to this problem is to code your file and send it to the receivers. But the problem is because we don't know the quality of the channels, we don't know at which rate we should code, and the traditional codes just allow you to send a file at a fixed rate, so they're not that useful for this problem. And we need codes that sort of adapt their rate according to the situation and are good. So the solution to this problem is our fountain codes. So what is a fountain code? So you assume you have that red file that you want to send, consists of a number of symbols. So what you would do is to encode it, and when you encode it, you create an infinite stream of symbols, and you just send these symbols to the receivers. Each of these symbols is computed independently and randomly. So then the receivers will each receive some part of this stream, and hopefully they're going to recover the original content. Some of them may lose a lot of packets, some of them may not. The point is each one hopefully will recover the packet as soon as they have received enough information. Of course, they need at least, for example, in this case, they need at least 4 symbols to receive the 4 symbols. Here, each of them have been able to do it with 5. Hopefully, I mean, the best is we can do it with 4, but maybe we cannot. The goal is to make 5 as close to 4 as possible. Um,
So we know when this is enough sender?
so, I mean, the point is, like the receiver may signal that, oh, I've received. If he has like a feedback channel where he can only send a bit back, then we're done. If it's not, that's some problem we have. I don't know. Yes. So, I mean, in the case where there is erasure, the receiver knows. In the case where there is not erasure, so perhaps the receiver has some estimates on the quality of every received symbol. This we assume.
So do I assume that each symbol is in an alphabet is large enough to contain log as many? I mean, one simple way I could do it, right? I could sort of flip a coin and sort of say, okay, I choose the case entry, and now I send you 2 bits, the case entry, and something which says it is the case entry.
So one solution is if your symbol is large enough that you can contain that bit, then like the information about that thing, then you are done. But of course, you also don't need to send all of the information. Maybe you can use some sort of pseudo-random generator to, I mean, it's not rigorous, but in practice it works, that to use some kind of pseudo-random generator to create the randomness with which you need to create the symbol. And another answer is maybe both sender and receiver are somewhat synchronized, and so they may have a shared seed with which they can create random numbers with which, from the time that the receiver received the symbol, he can sort of understand what kind of a symbol it is.
I think Christian just asked you, there is an extra header saying wow, this symbol.
Right, so you can't do it with...
I mean, but you can... Yeah. But no. But in the case that we are going to look at in the end, we're looking at the case where these are bits. And the bits are going to have errors. So you can't have a header of it. You need some form of synchronization.
But these are packets.
Yeah. But in the case where they're currently used in practice, they're packets and they have header, but still it's not a complete. So they use like they don't create all the randomness freshly. Okay. Okay. So here is the setting. This is just a review of what we said. Except that we just want to emphasize that we want this process to be efficient as far as possible, and we want it to be efficient in the terms of it's efficient to decode and encode, and on the other hand, it's we don't lose too much rate. The rate is close to capacity. So, I mean, having this model, it has a lot of other applications. Here is just one other application of counting codes, where instead of sending from one sender to many receivers, you send from many transmitters to one receiver, because all these are independent, so it doesn't matter from which server you're receiving this. I mean, you may download some file, at some point the server just crashes, no problem. You can download the rest of the file from someone else. So essentially, it's like a fountain where when you want to have water, it doesn't depend whether you have a glass, you just need to have enough water in it. It doesn't matter which fountain it comes from. And when does it come from? Yesterday, today, doesn't matter. So one efficient way to do this was proposed by Luby, although it's been done by Luby quite early, but it was published later because they were trying to patent and be sure to have it. So it's not that much new. It's like 7 years old. please. So what does Luby propose to do? So we want input symbols. We want to this is our message. So in order to create a new output symbol, first we choose some weight, and so we choose this with some probability distribution, which we call omega sub d. Here, for example, we have chosen weight 2. Then we choose d random messages, d random symbols, and so here we have chosen 2 random because d was 2, and we XOR them and we send it to the channel, and that is the encoder. So easy. The main thing is, what is this distribution omega? It really is important.
D is uniformly at random when you say d random or
No. According to distribution omega.
no. Assume I have d.
Yeah.
Then I choose each of the n choose d possibilities with the same probability.
Yeah. So average encoding time depends on the average size of d. So we generally want the weight to be small on average. That's preferable.
And you also don't want too big a variance, do you, or do you not care?
It doesn't care that much because we are going to send a lot of these things. So one example which is good for as an exercise before getting to the codes that Luby proposed are random linear codes where you are sending these output symbols are essentially XOR of a random subset of input symbols. Or in other words, you're taking D to be the binomial distribution. And then if you do maximum likelihood decoding, that is search for all possible messages and see which one is more probable, then it's easy to see that this is close to capacity. So essentially, we have a very good fountain code. The only problem is the computational difficulty of this, where when we have errors, it's very hard to solve its empty complete to find the maximum likelihood one. And even in the case of erasures, it's easy because you can solve it as a system of linear equations. You have a number of linear equations on the k input variables, but at least it takes quadratic time. It even takes quadratic time to encode it because the average degree is at least k over 2. So we are more ambitious.
Wait, so what is the symbol you send those on channel?
The symbols is the value of the bits.
So you assume that the sender and receiver are synchronized, they know.
Or the size of the packet is so large, the size of the symbol is so large that by adding that information, it doesn't increase it.
Wait, why did you need to synchronize?
If it's only bits that he's sending, and he doesn't have a header.
Yeah. So, I mean, generally, the way till now it was used, there was a header because it was erasure channel, and they could afford to have big packets. But when you have error, you can't have big packets. Yeah.
So I don't quite understand it yet. So you send one bit after time, and each time it's just the XOR of a uniform random subset of.
And the receiver knows what XOR this is.
Oh, we know.
Which one? It's synchronized.
He knows which subset this is.
Oh, okay.
So that's the
I mean, you're not actually proposing this, really. I mean, that's not the proposal. This is just analytically you can get it. It's not
No, I mean, when the packet is large, this is the proposal is essentially used.
Oh, it is? Okay.
But you're not proposing the synchronization.
No, but I'm not very. I'm not that good to know whether the synchronization can be used in practice or not. But yeah, this is. up to now, it's mostly a theoretical.
I remember the question in the past.
It's the same question, but just to clarify, in your code, you also send the subset of bits that you store, so the receiver knows which bit.
Yeah, we assume we know.
How do you assume that?
So I said, so if the size of the packet is large, then they really send that subset.
What if you have noise in that? What if you have noise in the header?
No. So you assume that the. Yeah. I mean, the internet gives you erasure. Problem is, it gives you erasure, but with a very high loss. But essentially, it gives you erasure.
But the number of bits you send is the same as the thing you're encoding, right?
What?
No, if the sets are big.
If the sets are big, it's still by doing, I mean, when you're sending packets, okay? First of all, the sets are not that big. Second, they use pseudo-randomness too. Okay. I mean, one work on seeing how, for example, if you send a simple arithmetic congruence pseudo-random generator for creating these subsets, how would that affect on the performance? And I believe they proved this is still achieves capacity for the erasure channel. So what is the point about? Okay, so so now that we have a low average degree, there is a chance that we can come up with decoding algorithms better than solving linear equations. Now we're restricting ourselves to the case of the erasure channel. So what is the LT decoding? So you have this graph where by now we all know that the bottom nodes are the output nodes and the top nodes are the input nodes. And here you see some output nodes whose degree is 1, so they really give the value of particular input node to which they are connected. So here this output node can reveal the value of that input node. And once that is revealed, then we can get rid of all the edges connected to that input node. And now we may have new output nodes of degree 1, and we can do this forever. Sometimes it happens that, for example, if you look at that, for example, if you look at that this guy, then actually this turned out to be useless because the value of that guy was revealed already. So the point is, we should try to decrease these useless guys because these are exactly the number of things that are overhead. So if we are, for example, getting k input symbols, then the number of these useless guys, the number of output symbols minus k. So we should try to remove these guys. And okay, so if we want to get a very good thing, we want epsilon to be small, and we call epsilon overhead. So the Luby has designed a degree distribution, which he calls the Soliton distribution, which is good because, first of all, it has a low average degree. It's logarithmic in k. And second, the overhead is essentially 0. So
distribution of the number b, is it?
Yeah.
So this is a distribution of? Yeah.
Mm-hmm.
So, and the point is, this average degree of log k is optimal because if we have average degree smaller than log k, then some input node would not be covered by the coupon collector problem. And so essentially, he has done his best.
What's the definition of overhead?
Is the epsilon with which we are quite sure we can recover the input with high probability. Yeah, so because we are looking at the erasure channel, we can assume that we have received everything. And that's exactly the point of fountain codes, whose performance do not depend on what is the quality of the channel.
Why do you call this, or why do we call it a soliton distribution?
It works on the fact that if you look at the number of input nodes at each point, which are ready to reveal themselves, then that number should be as small as possible. Because if it's large, then they may become useless.
Like soliton solutions of differential.
Yeah, yeah. Yeah. So if you look at, yeah, yeah. So exactly, if you look at that.
At the standing wave.
So if you look at those people who are currently ready to get there, it somewhat represents a wave. Which we want it to go with that exact. We don't want it to increase. We don't want it to decrease.
If it was not distributed for the continuous model, you will get epsilon which is 0. You will get just exactly one register related.
What's the advantage of this decoding compared to solving linear equations?
It's more efficient. So it's almost linear time.
You get a triangular. If this is solving a linear system, we get triangular like triangular and triangular and so on.
So one. So that is a Raptor.
Are you trying?
So.
He's a dinosaur.
What are we, right?
So the only difference between Raptor codes and LT codes is that they sort of try to get rid of this O log K, where we want to get essentially constant average degree. So the way they cheat to get that is so essentially he does not get. So it's the Raptor.
Raptor is an actual.
Good. Thank you.
So is that you do not recover all of the input symbols. Rather, you allow a delta fraction not to be recovered. And what you would do is you recover them using a precode. Before sending these bits, you precode them, and then you send them over a channel, and that's it. So you have a traditional precode to get is a little longer thing, and then you have an LT which is light. That is, the average degree is small, but which can recover everything except for a delta fraction of erasures. So the point is, you have constant average degree, but you have also constant overhead. But you can make that constant overhead small, as much as you want. But on the other hand, you will have to increase your average. You have to increase your average degree as well. By decreasing your overhead, you have to increase your average degree. But anyway, this is just a modified version of LT code. So if you're not happy, you can have the precode be a trivial code. So essentially, it works better in practice. And one good thing is that because the LT code is light, it will allow us to analyze it much easier. So I didn't give you an analysis of how Luby improved his code, because that's a little more difficult than what we will see in a moment. And then we will have linear time encoding and decoding. So essentially, you're getting linear time encoding and decoding, and you're achieving capacity over all of the channels. Yeah, for example, we can use like an LDPC code. But the point is, because the rate is very close to 1, right? like codes which have very close to 1, they're very easy to decode. There are a lot of them which are good. I mean, in practice, you may use even other codes rather than LDPC codes.
But the distribution there can be, you want something which decodes adversarial erasures or something, right? Or you need to understand what the distribution of those erasures are.
No, you don't need adversarial. I mean, if you know that if you look at every input symbol, it's decoded with probability delta, then with probability at most 2 delta, you're getting this 2 delta, right?
No, but that's the stronger statement, right? You're saying that you will have delta fraction erased arbitrarily. You're saying that each guy will be...
Yeah, so I mean, you can think of it in any way. I mean, this is just a general scheme of precoding. I mean, the way you can analyze it, probably, I mean, the way people analyze it is exactly find what is the distribution of delta, and exactly see for that distribution of delta, what is the probability that they get it.
It's not just a question of the distribution of delta, but which subset of delta nodes get erased.
Because it is random, then it doesn't matter. I mean, so
there's a random distribution of the output symbol. You don't apply an algorithm to it, figure out which of the blue symbols are blue and which ones are red. I don't think you can claim that these are going to be independent of blue with probability delta.
So because the LT code has been completely randomly chosen, right? So that delta fraction is going to be completely random. So you need to be resilient towards delta fraction random erasure.
And look at your bit and decide which one to erase.
The decoding algorithm does look at the bit.
No, so I think it's taken out into this code, shuffle the order of the Raptor.
And then do it.
And the main idea is we are essentially not looking at adversarial, because next we will see we're looking at Shannon capacity, not like distance. So, so here is the concrete theorem. I'm just saying it once, just to be to see what this distribution may look like. So if you have delta, where delta is supposed to be some very small number which you want to be, which is your precision, then the degree distribution is essentially this. So this is the generating function of the probability distribution, and mu is some small number. So you see that because mu is small, essentially there is not much vertices of degree 1, but there is like 1/2 vertices of degree 2, and degree 2, 1/6 vertices of degree 3, and so on and so forth. And this can decode almost everything. So, so here I'm trying to give you a proof, because this proof essentially also is good because we can. It's also it also works for other kinds of codes like LDPC codes. And if you've seen this proof, then you've seen like the proof of the way people analyze and analyze things in practice, like analyze sparse codes in practice. So the way we do it is to define another algorithm, which will be a message passing algorithm, and we will see that this algorithm and the way we decode it, the LT decoding, are equivalent. And then we can analyze the message passing algorithm. So what is the message passing algorithm? So the messages are passed between input nodes and output nodes, first from output nodes to input nodes, then from input nodes to output nodes, then back, forth, back, forth. So, so what are these messages? They essentially say, what do I believe about your value? So these the output nodes whose degree are 1 can tell about their belief about the value of input nodes. So you see them with black lines. So once they give this, now the input nodes have some information about what they have. So they can use this information to tell the output nodes, oh, I know this. So for example, if you look at x1, x1 tells this other guy, oh, I know my value. But you see, he doesn't tell his value to the guy who received his value from. So I never tell somebody, if somebody has told me something, I never tell him, oh, I know this because he has told me. The reason is later on we will see this helps us make the analysis much easier. So it gives us some form of independence. So, and it is obvious that okay, so now if you see this XOR node, because there's only 2 nodes that have been XORed. So, for example, if you look at this guy, he now passes his information, and we do this, so on and so forth. And it is obvious that this is essentially the same thing as we did last time.
Are you talking about non-erasure?
No, I'm talking about erasure. I really like erasure much more than non-erasure. So. So the point is, although this, but I think, I mean, unless we don't, I mean, everything we have about non-erasure is just the only cases where we could generalize the erasure channel. So that's okay. So in the end, you see all the input nodes have some black thing getting to them. So it's essentially okay. So everything is revealed, right? So how do we analyze this? The analysis is by tracking 2 numbers. One is pi, the other is qi, which is the probability that an edge is black at the ith round when we go up and when we go down. So the good thing is we can get a recursion for pi and qi, a coupled recursion, when we assume that the information that we receive from different nodes are independent. And when can we assume this? First of all, when we have a huge number of nodes. Second, locally the graph is tree-like for almost all of the nodes. And these equalities are actually not equalities. They are asymptotically equalities.
Oh,
but
okay, so it's not croissant. I mean,
which one?
is I really croissant?
When k is large, yeah. So this is just an asymptotic analysis. And we'll only do asymptotic analysis till the end. So, because it's very hard to do non-asymptotic.
What does it mean?
Do you have enough
analysis?
control over this that, I mean, do you have some kind of concentration? Do you have something to allow you to do this?
Yeah, that's essentially one of the good things that, I mean, this kind of concentration was first proved in the Luby Shokrollahi Spielman thing. And then it was generalized in certain settings by Richardson and Urbanke, where we will. Yeah, so.
Someone else.
Yeah, for example, in LDPC codes, they have to do martingale, but here even they don't need martingales to get this concentration. Right? We just need to.
The difference is because you're stopping at delta. What's the difference?
One of the differences is that, first of all, in the first paper where they needed martingales was they wanted the code to recover if, so it was a worst case thing. Okay, so they wanted to say that if our graph has this degree distribution, really has this degree distribution, not that we have created it with some degree distribution, then it will decode this error. So they needed concentration, but here we don't. So there the degree distribution was really, here we are trying to get that degree distribution, but with law of large numbers we're getting close to it, but not necessarily. So, and the point is, we know the value of, okay, so what are...
Now, there must have also been some condition on the distribution of t, some omega, such that...
So it's the sparse.
Concentration. I mean, if
so there,
down there,
it's very small. so we assume that the distribution is fixed.
Right. So you're assuming, because remember I said
So we fix the degree distribution, and then
if there was a big variance
In the degree distribution, you might be messed up. And
the degree distribution is, first of all, the degree distribution we assume is limited. I mean, is finite.
Oh, well, that's certain
Yeah.
point, not a big variance. Okay. So, good. Yeah.
But I mean, in the end, the right way to think of it is the case where it's not. But I mean,
make it
yeah.
too bad, I can find you counter. That doesn't concentrate.
Where the solutions of that are not what you think that, where it's not going to behave. So, I mean, at a certain point, like, I'm being picky, but at a certain point, you're wrong, right?
yeah, right. So anyway, so the point is, this small omega is a little bit different from the large omega in that it's the because it should we should choose a random edge, and then we see how many other edges it is connected to. Okay.
Nevertheless,
The big omega was really badly behaved. The small omega would also be badly behaved. Wouldn't concentrate. Yeah.
But I mean, it's you see why this equation. You have some idea of why these equations are true.
Can you remind me what black edges were?
What? Which one?
What the definition of black edges?
Black edges were the ones which we. So the point is, here when we are taking it, omega is a generating function, so it is multiplying these probabilities, and so we know that in an input node, we know that in an output node we are only going to reveal the value of that thing if the value of all those stuff are given to us. So it's an AND. It operates as an AND, and on an input node it operates as an OR. So we get these kinds of equations. Okay, so now we're going to get a view of going into erasure, to non-erasure, to errors. So what is our model? So we look at a channel which is memoryless, and first we assume it's binary, and second we assume that it's the channel works symmetric over 0 and 1, gives the same kind of errors on 0 and 1. Which is, and there are certain very interesting channels which are not symmetric, but we are focusing ourselves to symmetric channels. So one good way of summarizing, okay, so you can think of when you receive something from the channel, it's saying what is the bit, what the value of the bit is probably, and what is the probability that we are wrong. Assuming B is the correct bit, and this is our guess, P is the probability, and then the capacity can be calculated easily from the distribution of P. And also one convenient way to look at it is to define this log likelihood ratio, which is positive and negative depending on whether we are more towards B being 1 or minus 1. And also we will work with this constant Z where it just gives us the value of the log likelihood ratio if actually B plus 1 is set. Okay, so I mean, it's not that much important. So examples of these channels, one of them is the BEC, which we already saw. It's BSC and the Gaussian channel. All of these are symmetric channels. So by symmetric channel, we just don't mean BSC. More, we mean the Gaussian channel because it's more used in practice. So, and now we come to the algorithm for decoding. So the encoding is the same, but the decoding is a little different. Although because we have seen the message passing algorithm, it is not that much different from that message passing algorithm. Still, people tell to other people about their beliefs. So output nodes tell input nodes about their beliefs, and these beliefs are passed. This is why it's called belief propagation. So the beliefs are expressed in the form of these log likelihood ratios. So it's, for example, infinity, if I'm sure that it is 1, it's minus infinity if I'm not sure, and it's 0 if I have no clue.
Oh, well, anyway, it's minus infinity, not if you're not sure. If you're sure, it's not. But,
It's 0. Yeah. So, so these are the input messages where they receive all the beliefs from the output messages and somewhat summarize all those messages, aggregate all those information. And the right way to do it is to add those information, assuming that all those information have come from independent sources. This is very easy to see. The other one is that this is an XOR node. It has some belief of the value of Z0 and Z1 to ZK minus 1. It wants to know the value of ZK. So essentially ZK is XOR of Z0 to Z1, ZK minus 1. And if I am not sure about the value of something, if I don't know about the value of something with probability P, it is as if I don't know the value. I know the value of that thing with probability 1 minus 2P, and it's random with probability 2P. Because if it is random, still I'm with half probability true. And then, so I don't know the value of the XOR if and only if I don't know the value of one of them. So minus 2pk should be the multiplication of those guys. And if you write it in terms of the likelihoods, you will see that tangent hyperbolas should be multiplied. So still we can do the same kind of analysis. Here it's called density evolution. And although it's also been, I mean, it's not just being done by the group of more computer science people also did this kind of density evolution and proved rigorous results. But Richardson and Rankier showed that this density evolution is possible in a much more general setting. But in these settings, it was also shown by the Luby and brothers. So. So what is it? We are looking at the density of log-likelihood ratio messages from round to round. And
is Organte a physicist or a computer scientist?
He's an electrical engineer. Both are. So the good, interesting thing about this subject is that it was pioneered by theoretical computer scientists. So it was one of the subjects that really shocked electrical engineers because they didn't think these things could work this well, and so they were a little suspicious, especially, for example, these guys at the beginning. So the point is that, okay, so if you know that this density of messages that go from one round to another, then we can understand when we are okay. And the density works well on average, and we can get a recursive formula.
What's the density of the message?
The density of the belief that we send.
What's the fraction of new black edges? Is that what's the...
No, in this case, we are sending real values.
Oh, real values.
So is it a probability? I mean, what do you
The
mean
mean,
the
or what
density?
is it?
What do you mean? I'm asking the same question now.
So it's the density that we expect of the numbers that we see on the.
So it's just a percentage, you said.
Yeah, but it can be continuous, for example, in the Gaussian channel.
So it's the average percentage?
Yeah. And
right? Yeah. And so is this like the average of those numbers or something?
No, it's a density function. It's what is the probability? Yeah.
Oh, so my
distribution function, and you're going to get a convolution equation for this distribution function.
Yeah.
You're going to get like an integral equation, a convolution equation
Yeah,
for this.
exactly.
Oh, if I start with some
distribution function, I send you a message, and you have a distribution
And that's
function you convolute
and
with.
then you get the new thing.
Yeah. And it works
Can you
for
like break down
What is
Like-
the structure of the equation, just to clarify?
yeah. So for example,
Yeah, I know it's clear, but I mean,
let's say I'll write for one part.
Sure.
So let's say we have so bi was from output nodes to input nodes. So it's like this. Now we are interested in this. We want to calculate. Now we have the distribution here. We know it's di. We want to calculate distribution here, for example. So first we see what is the probability that here there are that many other edges. Let's say j many other edges. And so then because the j is equal to z1 to j plus 1 is equal to zj, then distribution of zj in this case is the convolution of, so it's di convoluted j times. And then because there is a probability associated, so there is sigma probability of j. This is the density that comes down, let's call it dr. And then on the other hand, on the XOR nodes, we saw that the tangent hyperbolics are multiplied, so their logarithms are added. Except that we should take care because there's sign, so convolution is over the group r times z2. So it's essentially again the convolution, but not over r, because we also have to work with the signs as well. We should take care of the signs as well. So, but it still is convolution. So, okay, so this works for a constant number of times, and we can, given a channel, given a degree distribution, we can exactly see what are these distributions are well defined. So it is a very well-defined question whether there exist degree distributions that achieve the capacity for every channel, whether there exists a sequence of degree distributions that achieve the capacity of the channel. And this is by far one of the most interesting theoretical questions in practical coding theory, because essentially the question for LDPC codes is very interesting because they are using these codes in practice, but they don't know whether it's working, whether they are achieving capacity or not. So one answer we give to this question is we can calculate the fraction of vertices of degree 2 using this formula. Oh, sorry. So if channel C has a capacity achieving degree distribution, then we know its value. And so this is the capacity, and this z is the z that was said is given that 1 was sent. So okay, so in particular this shows that you cannot have one sequence of codes, one sequence of distributions that achieve the capacity on all channels. I mean,
omega sub 2? What
He's just defining it there.
No, it's the probability that you have 2 degree 2.
No, yeah.
yeah. So for example, at least in this case, we see that brief propagation plus sparse codes is not as strong as maximum likelihood plus linear codes. It is not that trivial. So how do we show this? Oh, by the way, so here are a couple of values. First, it's interesting that omega 2 is bounded. It's in a very specific range. Not that. And its maximum value is for the erasure channel, which is 1/2. And these are the other values. This is actually the minimum value. So when the quality of the channel is very low, it gets its minimum value.
What?
Entropy noise.
Oh, the entropy. You mean like P or what is that?
P plus.
Yeah. Okay.
So to calculate the fractional vertices of degree 2, first, as an exercise, we look at the fractional vertices of degree 1. We're looking at Raptor codes. You see why we're looking at Raptor codes? Because using Raptor codes, we can do density evolution. With LT codes, things get harder. But essentially, we're only looking at the light LT part of the Raptor code. We're not looking at the decoder. So if you have some bit x, and you have two noisy observations of x, then the point is that the information you get about x looking at y and z is at most the information that you get using y plus using this. Here we are essentially using the fact that this is a noisy observation of x. For example, there are cases, for example, let's say y and z are random, and x is the XOR of y and z. Then the information we get from x given y and z is 1, whereas here the information is 0. So, but this is easy to see that when you have some value and you're getting different observations independently, then the noise is not that difficult. And if one of these is really so the point is if these amount of information that we get are both quite negligible, then this inequality is there's quite a large gap in this inequality. This inequality is really inequality. So this shows that omega 1 cannot be large. Because if omega 1 be large, then we have a number of output bits who are talking about the same input bits. We would have collisions. And when we have collisions, we have loss of information. Because we were expecting to get almost, when we are achieving capacity, we are expecting to get the information that that bit reveals together, in sum. So this shows that omega 1 should be equal to 0. By this I mean that the limit of omega 1 should be 0 in the degree distribution. So, so now what can we say about degree 2s? Let's look at the DEC first. So if you look at the all vertices of degree 2 and see which two input bits they join, and look at the graph these introduce, then this graph is important. In what sense? So if a vertex of degree 1 attaches to a node of that graph, then it will first all the connected component to which it is connected, because all those vertices are degree 2. So here one may think, so one may think that it's important whether that has a giant component, whether those guys over there have a giant component. And so if it has a very large giant component, then there is a chance that we get a output bit whose both endpoints are in the giant component. And in that case, we have certainly 1 bit loss of information. Right? So we don't want really giant components. On the other hand, it turns out that we cannot, we want at least something quite large. Because if it's not omega, okay, so when do we have giant component? When the average degree is at least 1, is larger than 1. So, and it turns out if the average degree is not less than 1, then because, as we said, we have very little vertices of degree 1, and in the beginning of the process, only vertices of degree 1 and 2 are going to play a game, because vertices of degree 3 in the beginning should have at least two of their neighbors revealed. So we should only, so essentially it turns out that vertices of degree 2 should be at least as large as 1/2. So this shows that the fraction of vertices of degree 2 should be at least 1/2. So, so we can get a similar threshold result for the general channels, where we can show that if omega 2 is bigger than the value we just proposed for omega 2, then the point is that leaf propagation would be successful in decoding to some extent. And when leaf propagation is successful, then we are in a problem, because if we a little decrease the fraction of vertices of degree 2, still leaf propagation is successful. And now if we add that little bit of vertices of degree 2, then that little bit are not given that little bit. They are giving a little less information to us. So, and on the other hand, if the fraction of vertices of degree 2 is smaller than that, then because we know vertices of degree 1 are small, then we are in a problem. So this essentially proves that the value of omega 2 should be equal to omega 2c. And the proofs of this theorem is easy. You just need to see that vertices of degree 3 have a second order effect. And it's very easy. Okay, so now one interesting thing, interesting idea Luby and Shokrollahi have is to use this approach to get other degrees. And the main idea is when you have an alpha fraction, when you have already revealed an alpha fraction of input nodes, still you should have an alpha fraction. I mean, still over that you should have a giant component. Not so giant, not very small. So, and using this, they get a number of equations. And if you solve those equations, then you will get this formula, and you're done. This is a very nice observation.
That's where you got the distribution, plus you added a little single.
This is one way of looking at, and the other way, I mean, I think Luby found it through that Soliton, I think, argument. But this is another way of looking at it, which was, I think, mainly observed by Descartes.
So is this true that there are many capacity frequencies, or?
No. So this shows that there is only this one. Although this I don't know to what extent this can be made rigorous. So, for example, I know that, I mean, to the extent I said this is heuristic, but they can make it into showing that this sequence achieves capacity. But I don't know whether...
Well, in the binary erasure channel for the, I don't know for the Rader's code, but for the original Luby et al. Paper, there are many papers publishing different distributions.
Okay, so the difference is here. So in LDPC codes, we know we have choice. We have both on the input side and both on the vertex checks. Here we know it's. Here we are. Yeah. So this is a neater way of looking at finding values, because we just need to reveal these numbers.
So when you said that there's no single capacity distribution, this is assuming on the input side you have the uniform distribution.
Yeah, and it seems quite, I don't know, for some reason having, it's not uniform, it's Poisson. But having Poisson on that size makes many of the calculations easy. I don't know. Maybe there's something there. So, okay. So this is something that we don't. So attempts to find capacity achieving sequences for non-erasure channels. So that is trying to solve that open question. So first, the main approach is to make certain assumptions and then see whether it can reveal some value for omega-3 and so on and so forth. But it cannot, because the main problem is we do not have a very good estimate on where these densities are going. So it really, and
What do you mean half the densities? You mean some equation for the DIs?
So it seems it seems like there's densities. First of all, move very slowly. So DI is not very different from DI plus 1. And it's
when we say we don't know the path of densities, is that you can't write down a convolution equation, you can't solve a convolution equation. I mean, what's
so you may think that you could do the same thing that we did for the BC for here. But in the BC, we knew what was the path. We knew that it started from we don't know anything. So the path was, right? So we knew that the path only, we know that the densities only have value over 0 and infinity, the log-lecture ratios. Either we don't know anything or... So the set of densities was, we knew which set of density. We could parameterize it by that alpha.
And alpha
was the number of fraction of vertices that was revealed.
Okay.
But here, the problem is we have this many different ways this path can go, and even we were very lucky that we could find the omega-2. So it turns out for omega-3, there is...
You have an equation in which, since you don't know that Z is trivial or what you have, or some, you don't know what the value of Z is, still you can write down an equation, you can get bounds on how things are behaving. I mean, just because it's not some function that you know, you can still get a lot of...
First of all, one problem is we don't know whether there exists really a specific path on which we are moving. So, I mean, we know it's discrete, right? And whether all of these converge to something, this is very interesting to prove that all of these converge to something. And it's probably the case that as we, the density evolution is fixed point on all of these paths.
Right,
but,
so you have
but
some
we don't
set
have
of
proof of all
equations
these
in
things.
Right, but presumably
If you had enough control over those
Still, it's not.
equations, then you could prove that there was a fixed point, right? I mean, you could put some assumptions on saying, okay, well, it's not BC, it's something else, but under certain conditions, then you would have enough tightness to get some kind of fixed point there. No?
You always get some kind of fixed point, but I mean, the distribution finally gets to its fixed point. But what I said is, probably it is the case that there exists one path in the space of all densities on which we are moving very closely. And if you take that omega, distribution omega, not to be finite, rather be infinite, which is, for example, the case where you said the soliton is completely infinite, then we are exactly fixed points at all of it. But still, knowing all these things don't allow us to calculate the omegas because there's too much arbitrariness there. So so but maybe there are certain things that helps us restrict the path. Okay, so now we go to, okay, so now we want to see what BEC gives us over. So if you use codes that are optimal for the BEC, that is those codes to which I showed you, what would this give us to? What would be the performance?
10 more minutes.
Okay. Yeah. So essentially, it's not that good, but not that bad. I mean, it's good in practice because you're sending it over any channel and you're getting like 10% overhead. It's much better than having to encode for that channel because the capacity is around 1/2, so you have to send 100% overhead. So it's not that bad. And okay, so one thing that will help us to do to understand how codes designed for BEC work over other channels is to get the general theory of how oblique propagation for the binary erasure channel works for other channels, and there are exact tight results. So we know upper and lower bounds in this relationship. This was already known. And it's curious. We're curious to see, for example, we can calculate exactly the overhead of a code, the exact overhead of a code that is capacity achieving on a symmetric channel on the BEC. So the exact overhead is equal to this value. And finally, okay, so this is the more interesting case is that, so now we are using the codes on BEC over other channels, and this is the bound and the overhead, which is not that bad because it's at least bounded. So even you're sending it on a very low quality channel, you have a bounded overhead. You might have to have a very large overhead. And it works like this, but in practice it's better than this. So in the end, it's at most like 43% or something, but in practice it's like 10% or more. And this is some further work which I already said. One is to calculate these degrees, the fractions. Second is to try to show some form of this fixed pointness, which is usually called flatness.
Because I thought
Had on the previous slide, but
Yeah, this we usually call.
So one,
flatness?
So if I think the idea has come from the BEC model, where if you write one kind of equation, then a certain function would become very close to 0. So it is, yeah. Here I had better not use this word.
Okay.
So and that to find the exact overhead.
Is that like his reaction to your talk?
So yeah.
And the other two fountains were.
So I didn't know the other two fountains.
On campus here, so we does campus the very first.
Oh, really?
Yeah.
So maybe because I checked on Google, then Google is so smart that they retrieve answers in your area.
Other questions besides when if we asked them. Thanks, Ellen.
Thank you.
You know what we should do? We should make arrangements, because we've only got 3 minutes. You will be done getting your teeth done at 2:30 tomorrow. Let's work with them from 2:30 to 3:30. You have physical therapy before that, so you're not even in. We'll try to work with them between 2:30 and 3:30 and then work with lots of okay? And I have to leave for 6 to dinner with Deborah, but you can go on.
So we both have.
You know what is weird, like so. I think it's better for us just to, you know, talk.
So we all work, you know,
That was just how it worked.